today's episode, we're going to be dissecting this contraption, an Obsidian Boiler. Now, why might you want an Obsidian Boiler? Power. Obsidian has a specific heat capacity of 0.111. Meanwhile, rock gas, which is what obsidian will boil into, has a specific heat capacity that is 5 times greater. This means that the amount of heat energy that we can extract from condensing the rock gas and then freezing the magma is 5 times higher than the amount of heat energy required to melt the obsidian. Now, technically, obsidian will melt into magma, but the melting temperature is higher than the boiling point of magma, so that magma will instantly flash to rock gas. So let's take a look at the details. First thing we want to look at is the heat source. For the heat source, we're using the exhaust from hydrogen rockets. Hydrogen rockets produce 2 forms of exhaust. The first form is steam. It comes out at a temperature, I believe, roughly 3,800 Fahrenheit. That's too cold to melt obsidian. The other form of exhaust that comes from hydrogen rockets is in the form of pure heat energy. This heat exhaust is produced in a 3x9 area rectangle directly beneath the hydrogen rocket engine. The first 2 tiles are inaccessible to harvest because we have to have a rocket platform. The third is also inaccessible because we need to create the top of our insulated box. Now, the material used here to create the insulated tiles is insulation. Every other material will melt. Inside of the heat box, we have a couple of spikes of diamond window tiles. This is to help capture and spread the heat around. We also have several diamond temperature shift plates for the same reason. And then inside the box, we started with supercoolant, which eventually boiled to become gaseous supercoolant. You don't have to use supercoolant here, water will work fine. And then finally we have, within each diamond heat spike, a row of wolframite mesh tiles, and this is just to enable the gaseous supercoolant to flow between the 3 sections. Wolframite here is the only material that won't melt for mesh tiles. Steel will melt, and that's the only other material you could consider. I guess you could also consider thermite, but the thermite would also melt here. So wolframite is really your only option for materials for mesh tiles. Beneath the heat box, we have a row of wolframite mechanized airlocks. Again, here, wolframite is the only material that won't melt. Steel will melt, thermite will melt. And beneath this, we have a row of diamond window tiles, where we're running a conveyor rail of obsidian to perform the actual melting. Beneath the heat box, we have a chamber where the rock gas will form once the obsidian boils. Within this chamber, we have radiant liquid pipes filled with liquid uranium, and this is being used to condense the rock gas to igneous rock. At the bottom of the chamber, we have another row of diamond window tiles. This is to help make sure that once the rock gas condenses, that it will freeze to igneous rock and not stay in a magma liquid form. rock gas is frozen into igneous rock. We extract the igneous rock with a couple of auto sweepers. You may have seen rust melter or regular melter designs where the auto sweeper and conveyor loaders are located within sort of the vacuum chamber where the condensing or freezing is happening. That won't work here in our Obsidian Melter because the temperature of the rock gas exceeds the overheat temperature of an auto sweeper or a conveyor loader when made of thermium. So instead, I'm using a game mechanic here where an auto sweeper is able to pick up materials through a wall when the tile in the corner of the wall is missing. You can see here this auto sweeper is able to grab rock from these two tiles. This auto sweeper is able to grab rock from these two tiles. The igneous rock, once it's picked up from the conveyor loaders, is sent through this heat exchange. This temperature heat exchange consists of a set of thermium metal tiles that are in a vacuum. The outgoing igneous rock is sent down the heat exchange into the steam room. The incoming obsidian is sent up the temperature exchange into the melting chamber. The conveyor loaders here are made of tungsten. The reason I chose tungsten rather than thorium or steel is to reduce the temperature transfer that occurs between the conveyor loaders and the hydrogen atmosphere that is in this room. Tungsten has a lower thermal conductivity than thorium or steel, even though it has a lower overheat temperature. So you can avoid overheating by keeping this room cool, which we already need to do because we have a couple of steam turbines in it. And that way we can reduce the heat exchange between the hot igneous rock that we're collecting from the melting chamber with the hydrogen atmosphere. The reason we want to do that is to make our temperature transfer as efficient as possible. The steam room itself is pretty typical. There's nothing special. The odd shape you see here is just because I was trying to squeeze the contraption up against the side of the map. You have a little bit more space. You don't need to have two separate rooms for your steam turbines. You can just have one room with your steam turbines and your conveyor loader and auto sweeper, and one layer of steam in your steam room. The only thing that's potentially unique is at the bottom layer of the steam room, I have a row of tungsten metal tiles, some mechanized airlocks, and another row of tungsten metal tiles. This section here is being used to keep the liquid uranium that's being used to condense the rock gas at a appropriate temperature. We want to keep the temperature below the freezing point of magma, but not so low that it erodes the efficiency of our temperature heat exchange. Taking a look at the plumbing overlay here, we can see that the liquid uranium will zigzag through the freezing chamber, come down through insulated pipes to the bottom of the steam room, and then traverse this row of tungsten metal tiles here, and we will extract heat from the liquid uranium by closing these wolframite doors here. That temperature is controlled by this liquid pipe thermal sensor. And I have it set to 2800 degrees Fahrenheit. And this will keep the liquid uranium between a range of about, I've seen it go as low as 1800 degrees and as high as about 2500 degrees. The reason that you want to use tungsten metal tiles here and wolframite doors is actually to minimize the amount of heat transfer between the liquid uranium and the steam room. If you use steel or thermium, you'll actually get too much heat transfer and your liquid uranium will become too cold. So you want to use tungsten or perhaps gold to minimize the heat transfer. You want some heat transfer, but not too much to keep that liquid uranium at a range that makes sense. Going back to the cloning overlay, other than the loop of liquid uranium, we also have a cooling loop where you have your standard aqua tuner and supercoolant setups to keep your steam turbines cool. And then the output of the steam turbines just collects the water and dumps it right back into the steam room. Pretty standard here, nothing special. Let's take a look now at the shipping overlay. We have a incoming rail of obsidian. This traverses up the temperature heat exchange and is sent to the top of the melting chamber and will circulate in a loop in this melting chamber until the obsidian actually melts. To control the opening and closing of the mechanized airlocks to add or reduce it, that is done with the conveyor rail element sensor. We have this set to detect obsidian. So whenever it detects obsidian here, that means that the temperature is not high enough to melt it. And if it does not gauge, it will engage the mechanized airlocks. When the rail is empty, it will not detect obsidian and keep the doors open to prevent excess heat from being transferred to these diamond window tiles here. The incoming rails are not fully saturated with obsidian. This is for two reasons. The first is that we want to make sure that the contraption is fully sustainable. In the game, there is one source of sustainable obsidian. Obsidian can be harvested from the Metallic Asteroid field. The Metallic Asteroid field is made of 70% obsidian. And in your playthrough, the maximum mass and the refill rate will vary slightly. But on average, you can expect to be able to extract around 600 kilograms per cycle, which works out to about 1 kilogram per second. In our contraption here, we're limiting that incoming obsidian to a little more than 1 kilogram per second using a conveyor meter. Slightly more than a kilogram here because occasionally the obsidian will not immediately melt when it hits the window tiles. So you won't get full throughput of 1¼ kilograms per second. You'll get slightly less than this amount. Second reason is you don't actually need that much obsidian to melt to generate a lot of power. Slightly more than 1 kilogram a second, as we can see here, is enough to keep 4 steam turbines running almost full time. 2 of them run full time. A third runs roughly about 90% of the time, and then the fourth runs about 70% of the time. Power-wise, there's nothing special. We have a couple of connected to our main grid, a couple of circuits via large power transformers. This is just to minimize the temperature exchange between the steam room and the steam turbine rooms. You could just use a heavy wattage conductive joint plate and skip the large power transfers and just run heavy wattage conductive wire everywhere. But to minimize the heat transfer between the steam turbine rooms and the steam room, instead using large power transformers where the output of the steam turbine is connected to the high side of the transformer, and the low side of the transformer is connected to the main power grid. And that's it. I hope you enjoyed today's episode, and thanks for watching.